Okay, let's read the question. Which choice describes data from the table that support Barrett and Rayfield's suggestion? So I need to support their suggestion, and that means I'm going to go ahead and read, figure out what's going on, and figure out what their suggestion is. The largest Tyrannosaurids, the family of carnivorous dinosaurs that includes blah, blah, and most famously T-Rex, are thought to have had the strongest bites of any land animals in Earth's history. Determining the bite source of extinct animals can be difficult, however, so there's a problem with determining this bite strength. And paleontologists have suggested that an estimated dinosaur bite force may be significantly influenced by the method. Okay, so different method will get different estimates of bite force. So what do we have? We've got different studies at different times, and they're different methods. Well, actually, these ones are the same method. So these guys have the same method, and their estimates are about the same, whereas the other methods are different, right? So that's good. That's consistent. Within a method, the estimates are the same, but across different methods, the results are different. So I think I get a sense of what we should be looking at for the answer. Let's see what supports this suggestion. The study by Mears uses body mass scaling and produced the lowest estimate of bite force. Well, the study produced the high. No, it's not between the minimum and the maximum. That's not the idea. It's a question of whether the change in the bite force estimate depends on the method. B, in their study, Gignar and Erickson used tooth bone interaction analysis to produce an estimated bite force range of, again, it's not what the min and max were. That's not the question at hand. These may well be true. In fact, I'll go up. Yeah, it is true. For Erickson, it's 8,000 to 34,000. This is true. But as typical, it's not relevant. Typical for a wrong answer choice, that is, on the data or table questions. C, the bite force estimates produced by Bayes and Falkingham cost. Okay, I think those are the two that were together. Yes, these are the two that had the same method and the same value. So these two were similar to each other. This is looking good. While, that is whereas, the estimates produced by Mears and Ginnak, the other two, were different, and each differed substantially. This is the right idea. C is going to be our answer. Let's just read D real quick. The estimated maximum bite force produced by cost exceeded the estimated maximum produced by Bates, even though they used the same method. Yeah, the estimate was not that different on the maximum, and that's really not addressing the answer to the question. So again, this might be true, but not relevant. The suggestion we have to support is the idea that different methods lead to different results. And within a method, you get the same result, which is corollary to that. Okay, let's read the question here. Which choice describes the data in the graph that support Meng's conclusion? So we're supporting with data in the graph the conclusion. Let's read what the conclusion is. Aerial robots vary considerably in their holding force. The ultra-fast robot hand, for example, has a holding force of 56. So I'm not sure what holding force is, how much it can carry. Ultra-fast equals 56 holding force, okay? More than twice the permanent magnets. Permanent magnet would be like 28 holding force. And more than 4 times the Yale Model T, which would therefore be 7 holding force. Since an aerial robot must lift its own weight along with its cargo, engineer and colleagues used a ratio of each robot's holding force to its weight. So holding force to weight equals payload capacity, okay? With higher ratios corresponding to greater capacity. So yeah, it'll hold more given an amount of weight. Concluding that the ultra-fast robot's hand is a higher payload capacity than the Yale Model T. So we must support their conclusion. So their conclusion is that the ultra-fast 8PC here of ultra-fast is greater than the payload capacity of the Yale Model T. Yeah, that's going to be true, right? So what do we see in the graph, we see the ultra fast and the Yale Model T have about the same weight. Okay, they have about the same weight, but the holding force of the ultra fast is about 8 times the holding force of the Yale Model T. So it's going to have a much higher ratio of holding force to weight, or PC. So the ultra fast robot hand and the Yale Model T each weigh more than, not the fact that they're more than 450 grams, right? Now, a student might jump on that because what is the important thing is that they're both about the same. And they are both just more than 450. But the key idea is not that they're above that threshold, because they could be above that threshold and very different, right? They're not, though. This is not quite the right idea. That could catch a few students. The ultra-fast robot hand and the Yale Model T each weigh more than the permanent magnet. Well, we know that. That says nothing about our conclusion that the ultra-fast has a higher payload capacity than the Yale Model T. The Yale Model T has a lower holding force than the permanent. No, it has nothing to do. That's the wrong comparison. A false comparison, as we've seen so many different types of answer choices. The ultra-fast robot hand weighs only slightly more than the Model T. Yeah, they weigh about the same. That's the key. The one has a much higher holding force than the other, but they weigh about the same, so the PC ratio is going to be much higher for the ultra-fast. All right, D is the correct answer here. Which choice best describes data from the table that support the student's argument? So strength and weaken, we're going to support the student's argument. So here's going to be his arguments, usually at the last sentence. And let's read the whole paragraph to figure out what's going on and what is the argument. Native to Latin America, the cane toad was introduced to Australia in the 1930s. So it's from Latin America, but it went to Australia. In recent decades, tadpoles in the Australian population have been shown to consume eggs of their own species. A 2022 showed that when presented with cane toad eggs, as well as eggs of native Australian amphibians, cane toad tadpoles disproportionately consumed eggs of their own species. So this weird Latin American cane toad ate its own eggs. It didn't eat other amphibian eggs. This behavior resulted from their attraction to something, a chemical produced by the eggs of cane toads, but not by the eggs of native amphibians. So that suggests this is what the attraction was. However, here's our contrasting ideas we often see. Using data from this study, a student wishes to argue that the presence of bufadinol doesn't entirely explain the cane toad tadpole's preference. So something must in the table show that there's not just a clear, straight relationship between more bufadinol and then more eating of your own species eggs. Let's take a look. What is this table telling us? So a percentage of available eggs eaten by cane toad tadpoles. So, okay. And we have other kinds of toads, including its own. So it eats its own a lot more, okay? Those are the only one that's not native to Australia. That's not really important. And it produces butterfly. It's the only one that is important. Okay, so this actually shows that it eats mostly its own, indicating that this presence of the chemical is causing it. So what might create an argument that it's not the entire explanation? Well, if it were the entire explanation, you might expect all the other toads to be about the same. In other words, they all don't have this bufadinol or bufenolide or whatever it is, right? So why would there be differences that one or two of them are only getting 1% versus, say, the 7 to 10%? There's something in these frogs that's causing more attraction to their eggs than the little red tree or the dainty green frog. So there's something else going on here. I think that's going to be our answer. The tadpoles consumed a higher percentage of the striped burrowing frogs than they did the eggs of the dainty tree frog. Yeah, that is the difference, right? So that could support it. That could be an example. Maybe. I'm not going to choose that yet. The tadpoles left a certain percentage of the eggs of each of the 5 species unharmed, thus ultimately allowing them to hatch. Well, this says nothing about what they left unharmed. Is that information even in the table? No, it's not. I guess it would be the converse of those. So if there's 10% eaten, 90% uneaten. So, okay, yeah, I guess that is in the table. The tadpoles left a certain percentage of the eggs of each of the 5 unharmed, thus ultimately allowing them to hatch. Well, that's still not important. It's not relevant, okay? There's no relationship between those particular percentages. It's obviously, that's not it. C, the tadpoles consumed a lower percentage of the short-footed frog eggs than they did the eggs of their own species. Well, of course they did, because they don't have the bufalidide or whatever, okay? D, the tadpoles consumed the same percentage of the dainty tree frog as they did at a little. Okay, so those were the two 1%. It's not the fact that the 1% are the same. The issue here, it is A. It's that a couple of them, the short-footed and striped burrowing frog, had a higher percentage than the other couple, the little red and the dainty green. And they only gave an example of one, the burrowing versus the dainty green, but it's the core idea. Why is one 10% or 7% and the other one is only 1%? That makes no sense because they should be about the same. Neither has that special sort of bufalidide or whatever it is, okay? Yet they're very different. So something else must be going on there. Therefore, the answer is A.